Hi, I'm Mark Wilson, the Engineering Heretic, and this is the last in the series of designing gears. Of course, we'll be looking at Unwin's last section in his article in Model Engineer about clock gears, and I'll explain to you the difference between regular transmission gears and clock gears. Now, according to Unwin's chart here, there's two charts, and we're only dealing with, oddly enough, this particular column down here, which is the metric module 1. And there's a couple of other things going on here, but I'll talk about those in a minute. And there's also, one is for the pinion, which is the smaller tooth, the smaller the pinion, and then there's the wheel, which is the larger one. Normally the pinions are hardened steel and the wheels are brass. Okay, now there's various changes in this. There's some subtle changes in gearing with clocks, and let's just first of all have a look at why things are a little bit different. I'll have a look at my CAD model. This is a model of developed from Unwin's charts and what have you. We have a wheel and we have a pinion, and you'll notice here that the wheel, this is about 3 millimeters wide. We're dealing with metric module 1, of course, and of course you can change that to anything you like, just the same as the previous gears, but these are not transmission gears so much anymore. These are used in a different way, and in clocks, from the spring drive in a clock or a weight-driven clock, the first wheel, which is off the spring, comes off that one there. It's driving a pinion, okay, which then drives another wheel onto another pinion, and so on and so forth, all the way down to the escape. So effectively, not so much transmitting power like in regular transmission gears, but this is a transmission of a movement and a step up, sort of something like about 200 or 1 to 200 step up through the train. And of course, the wheels, because they're brass, we're using dissimilar metals. We're using steel for the pinion, which is prone to wear because it's doing so much work, but the brass ones are of a dissimilar metal, and therefore that's the way you lubricate this, by two dissimilar metals, so they don't sort of stick together. And of course the pinion is hardened and the brass is just less soft. Now pinions, if you have a look here, you'll see that the pinion is substantially wider than the wheel, which is very common in clocks. Let's look at the profile. I'll look at this front on, and we'll zoom in nice and close so you can see what's going on here. The wheel, if you look at the profile of these teeth here, they are what we call ogival in shape. Now, look at the top, it might be a little bit easier to have a look at. An ogive shape is something you'd see like on a church window from, say, about the 1850s or something like that. Stone churches with their windows with this curve reaching up to a peak at the top, and that's called an ogive shape. And the wheels on these are basically, the teeth are quite long and skinny, reaching up very high, and they're slightly different to the pinion. So let's look at the pinion. You'll see the pinions are narrower than the wheel by a substantial amount, and they're a little bit blunted and shorter in length. And if you see them running together, you'll notice that there are lots and lots of clearances with clock wheels and pinions. And that's because there's no real lubrication, any little speck of dust that gets in a clock movement will cause all sorts of issues, particularly at the end of the train towards the escape. Any little bit of dust will stop the clock from working. So there's lots and lots of clearance and lots of depths in things, so that the dust just basically falls out of the movement. And effectively, they don't do much work at all. The hour handle, the ones near the spring, are barely moving at all. And even towards the escape, they're only doing maybe 1 or 2 turns per minute is about the maximum RPM. In these strike trains, of course, there is a lot more movement going on, and you hear that whirring sound from a wheel and a pinion and a clock when you hear the strike train going. And that's because there's lots of rattling between these gears, causing that sort of whirring sound you hear when a clock starts striking a chime or something like that. Now, weirdly with this one here, I'm using Unwin's chart, and I've developed a wheel and a pinion from this, and I've actually changed it a little bit because some of his charts are a little bit hard to read, but I've developed a wheel and a pinion based on Unwin's charts. So let's have a look at how this works. We'll go into this particular one here. We'll edit this in a separate window. There is my my pinion, and if I look at the sketch that created that particular shape, there it is. There, you can see I've developed. Look at that big bit. You can see that this size of these teeth here go right the way down to the center point there, so they're sort of tapered in, and there's the ogival shape reaching up there, a little bit more blunt than the other ones, and these teeth are narrower, and the depth is slightly different as well. And of course, we'll get out of that. We'll see the go to the last figure, and this is a 6-tooth pinion. Now, 6 teeth is the smallest number you could ever go with a clock pinion. They don't work less than 6. Normally, they're up around about 8 or something like that. But just to show the difference there, you can see the variations there. So that's the, and of course, I think this diameter here is only about 1.5 mm diameter, so it's almost unserviceable as it is, because the shaft, or the arm of the shaft that goes through there, would be quite small and very difficult to manipulate. There is one slight variation on this particular one. I'll just show you what the difference is. Sometimes in American clocks, you'll see this ogival shape will be completely round there, and we call them lantern pinions when you're just using pins mounted on a brass sort of little hub and using round pins rather than something like that. We call them lantern pinions, but effectively that would be the center point there and completely round and driving a wheel, just the same as these ones would, but that's just a variation of that. Let's the last figure, and we'll get out of that one there. I'll leave that one there. We'll go back to the wheel, and let's have a look at the wheel. We'll edit that in a separate window. And we'll have a look at the sketch that made that. And we'll zoom in a bit closer, and you'll see here, this time the tooth are just vertical. They don't go to a center point there. They're slightly higher, slightly deeper in there, but a wider tooth than the pinion. And of course, we'll get back out of that. And generate that to the last figure. And we'll leave that one as well. So you can see here the movement, the clock movement. It's basically a wheel and a pinion. That's a 30 tooth. This is a 6, and that would be what you would see in clocks. And vastly different than transmission gears, because transmission gears transmit power, but these are just transmitting a little bit of movement and with no lubrication at all. So the criteria is a little bit different. And that is clock wheels and pinions, all developed from Unwin's chart you see here. I have modified this just a little bit to suit myself, and that's what's the beauty about having a CAD system, is that you can modify things to suit what you want and see them before you make them. And I'm Mark Wilson, and thanks for watching.